Hi, everyone. This is Rob Gray from ASU and the Perception Action Podcast again with another review of an article from one of my favorite articles from 2020. In this article, I want to talk about control laws and kind of what shapes which control laws we use for a given action. Right. So in the ecological approach to action, it's proposed that the way that we control our action is establishing a control law. So a coupling between some information source in the environment and some parameter of our movement. And this is illustrated in this kind of with a lot in detail in here with this diagram from Bill Warren from his excellent 2006 paper, The Dynamics of Perception and Action, which I'd highly recommend. And what I want to try to illustrate here is, ask the question, what shapes the emergence of which control law we use? Because essentially we're at Bernstein's degrees of freedom problem again, right? There's a multiple possible ways I could move to throw a ball or hit a ball. How do I then decide which one to use? What are the factors that shape the control law that's going to emerge, right? Some control law is going to emerge through our experience, our practice, the influence of the coach, and so on. Well, there's several factors, right? First, it's going to depend on the information that's available, right? That's going to shape it. It's going to depend on which aspects of our movement we can control, right? Can we control the velocity of our movement, the force, the amplitude, et cetera, and so on. But the factor I want to focus on today is an interesting one that was looked at in the study is what we want to also do is have a control law that has a good degree of what is commonly referred to as error tolerance, right? So what do we mean by that, right? I put this in quotes because it's not really a term necessarily we associate with ecological approach, but it captures this basic idea. So back, I think, for article number 2 of these ones I talked about the relationship between movement variability and outcome variability, looking at a study of baseball pitching, right? So what was shown in that study is that baseball pitchers seem to the way that they move, they have this covariation, these motor synergies between the movements of their different body parts, the different joints. They compensate for each other. So if the angle of the knee is a little wider on one pitch, it's compensated for by having a bit smaller elbow angle, etc. So on. Right. So we have this motor synergy, which helps to make our outcome. In that case, it was the hand position more consistent. Right. So repetition without repetition. We're producing a consistent movement outcome, the position of our hand at the ball release, by having covariations and motor synergies. But the important point I want to make here is even with a highly skilled athlete that's developed these synergies, this highly functional motor variability, right, there's still going to be variability in the movement outcome, right? In this graph is showing you, if we just look at these ones, this is actually the covariation. You can see it's not zero, right? The standard deviation of hand position is not zero. There's some variability, right? There always will be, right? We're never going to be able to produce the exact same outcome every time. So what we want to do in the control law that we use and the one that emerges, we want it to be tolerant to this variability, right? Tolerant to the fact that we're not going to be able to produce this exact same hand position when we release the ball as a pitcher. And what we're going to see is there are different strategies, different ways, control laws that we can use that actually are more and less effective at minimizing the tolerance to this variable. By tolerance, I mean the relationship between the movement outcome and the performance outcome, right? So we want the performance outcome to have low tolerance, high tolerance for variation in the movement outcome, right? So we don't want slight differences in the angle of the hand position to have massive changes on where the ball goes as a pitcher, right? So that's what we mean by error tolerance. So this study looked at this question in the context of basketball shooting, free throw shooting, a study by Nakano et al. Published in Human Movement Science, right? So what they did in this study was they did some measurements and also some modeling. Very interesting, right? And what they showed first is that if you look at the basketball free throw shot, right, and you model it in terms of two parameters, the speed at which you release the ball, okay, and the angle at which you release the ball, What this creates is a manifold, right? So it creates this. What this shows is the essentially range of different possibilities you could use for these variables and still get the ball in the net. The yellow, anything in the yellow area would produce a swish, right? So I can shoot the ball at 7 meters per second with an angle of 47. So very of a like kind of a slow speed at a low angle, or I can shoot the ball at a very high, much higher speed, 7.5 meters per second at a much higher launch angle, right? So I have this, again, this is kind of a degrees of freedom problem. I have these range of possibilities I could use defined by this manifold, right? And these shots would go in but hit the rim, right? This is from modeling they used to produce that. So the question is here, how do we know where to be in here, right? What do we do? What control law do we use? What are we going to do? Are we going to shoot at a low speed or a high speed? We're going to shoot at a low angle, high angle, right? So that's the question. This is the possibilities. You can think of this as a solution space. So what they did in this study was to take 8 college basketball players. So, if you want a critique of the study, that's kind of a low number. For what they were doing, it's not super critical. This is kind of an exploratory testing some ideas. So they're not trying to say that everybody is using the strategy, but it definitely would have benefited from more participants and maybe different levels, but that could be future research. So they had these players, though, they shot free throws, right? 53 throws while they were motion tracked. Okay. They used they used quite extensive modeling of the ball flight, right? They looked at a bunch of different parameters, and kind of in pilot studies, they realized, they could model it basically just based on the release and the angle, right? That captured enough of the variability. They measured things like spin and other things, position, release position, how high above your head, but those really didn't include those in the final model. Okay. So they're going to look at these. And basically they want to look at what do people do, okay, when they shoot the basketball. And so here's what they found. So here are the results for 6 participants. Okay. So each different participant, these are, again, the solution manifolds, right? So the solution manifold is based on each individual, what kind of range of speeds and shots they do, right? So what you can see here is that for most of the participants, the red dots are the actual shots. Most of the participants are releasing the ball at the lowest, almost the lowest possible speed they could and still be in the manifold. So look at this person is releasing at about 7 meters per second. This person's, again, 7 meters per second. This person way down at the end of release. So they're all at the almost the lowest release speed they could get away with and still be in the manifold. Only exception, maybe this person's doing something different, okay? But it's important to point out that what they found is the people that shot the best all did this strategy, right? So they all seem to be using control law, which involves minimizing the release speed, right? To keeping that as consistent as possible, keeping that the minimum the release speed as low as possible that is allowed for, and still make the shot. Why did they do that? Why was that the control strategy that emerged? Well, there's a couple of reasons. One is just kind of the general rule that of what's called signal dependent noise, right? Smaller signals have less variability generally, right? If I took a bunch of people and measured the size of their big toe, there's going to be smaller variance, right, than if I measured their height, right? Smaller things have variance is usually proportional to the size of the signal. So by shooting at a lower speed, there's less noise in the motor system. Okay, less. So it's going to be more consistent than trying to shoot at a much higher speed, right? At least for that parameter. Okay, but more importantly, what we can see is from their other kind of model is the error tolerance, right? So what they did in their paper is actually modeled the error tolerance. So what we have here is this is for one participant, right? You can see all their shots in red dots here, right? What we see here is they're shooting they're shooting at the lowest release speed, that kind of strategy. What you can see over here is this is showing the amount of error, right, for different release angles, right? So what you can see, they're shooting at the release speed of 7 meters per second. To shoot at that release speed, they need to shoot at an angle of about 50. What you can see here is this green line shows what they call the propagation of errors, and I'm not going to get into all the modeling here, but what you can see is 50 is a really good spot to be, right? Because if you have a variability in the outcome, terms of the angle you release, right? Remember, like we said at the start, the movement outcome is always going to vary a little bit. Okay, so if I release 1 degree less than my goal, it's hardly going to change the error at all. If I do just 1 degree more, so sitting at 50 is a great spot for error tolerance, right? Moving around 50 doesn't change the error much. If I shot up here at 7 degrees, right? There's a big error tolerance, right? A slight change there's no error tolerance. I mean, if I slightly change my angle, I'm going to have a very big increase in error, right? And you can also see this on this graph, right? Shooting down at 7 meters per second allows me to have some noise and variability in my angle of release. Shooting up at 9 degrees is not going to allow me. I'm going to be out of the manifold very quickly, right? So this error tolerance is one of the main reasons likely people this strategy emerges, right? Shooting at a lower speed allows for more tolerance in the inevitable variability in the movement outcome, right? So it's a factor that's going to shape. Interesting, and then they did more modeling of this if you want to look at the paper. Interesting, what they found is one idea that people have had about how we take into account this issue of error tolerance is what I could do is each person could move, right? So I've said this in a few of these reviews now. Everyone has their own inherent variability, right? People vary. Some people have a lot of variability. Some people have a little variability, right? And you can see this in this person, these two people, right? This participant E has a really small cluster of shots, which creates a really narrow manifold. This person has a huge spread of shots, many of which are outside the manifold, that creates a much wider manifold. So one idea that they actually tested, and if you want to look at the paper, is that people could choose a different control law, right? Choose meaning not meaning consciously, but means different control law could emerge based on their own inherent variability. So people could control and use different release speeds depending on their variability to pick the one that has the most error tolerance. So for this person over here, the lowest error tolerance is right down where they are, right? This person might be down. So the people might have different regions of the manifold to sit depending on their own inherent variability to kind of optimize for themselves. But there wasn't really evidence of people doing that in this study, which I think is a really interesting question. Okay, that's it for this presentation. I think I'm going to have a couple more of these reviews to wrap them up. So watch out for those. Thanks for joining me, and cheers for now.